Section 2.2 Circles inscribed in polygons. In last section, we talked about a polygon inscribed in a circle. So in this section, we talk about the other way. So first, look at the definition. If a circle is inscribed in a polygon, the circle is tangent to each of the sides of the polygon. So if we look at this picture here, the polygon can be a triangle which has 3 sides, or a quadrilateral which has 4 sides, or even a pentagon with 5 sides, and so on. So in this picture, it's a quadrilateral. So it's a polygon with 4 sides, and there's a circle inscribed in the polygon. And if we look at each side of the quadrilateral, the circle is each side is tangent to the circle, or you can say the circle is tangent to all the sides of the polygon. That means if we look at the point that the circle and is tangent to the side, and we join the center and this point, it's going to be perpendicular to the side. And next, we can also say that a polygon circumscribes a circle. So a circle is inscribed in the polygon, or we can say a polygon circumscribes a circle. And we can also say this polygon is circumscribable, which means when we have a polygon, can we inscribe a circle in there? And the last section we talk about, when we have a polygon, can we have a circle such that the circle inscribes the polygon? So these are two opposite type of questions. The first theorem, it says the angle bisector of any triangle intersect at a single point G, which is the center of the inscribed circle. So if we have a triangle and we try to draw an inscribed circle, and so there's the center of the circle is going to be the intersection of the angle bisectors. We in one of the sections, section, I think it's section 1.2, we talked about the median of the triangles intersect at a certain point. I'm sorry, it's section 1.3 on page 52, theorem 1.32, property of medians. Median means we take the middle point of each side and join the opposite vertex, so we get 3 medians, and then we have proved in theorem 1.32 on page 52 that these 3 medians are concurrent. And we also proved that the distance from the intersection point to each vertex is 2/3 of the length of the median. In this problem, it's a little bit different. It's not talking about a median, so we are talking about angle bisectors. So we have, in a triangle, we have 3 angles. Each angle, we can draw an angle bisector. So we have 3 angle bisectors. And then notice that this angle bisector may not be the median, because this line segment bisects this angle, but it doesn't mean this point here is the middle point of AB. So the median and the angle bisectors are different. But the properties of angle bisectors kind of similar to the property of medians. So the 3 medians are concurrent. Here, the same thing. We prove 3 angle bisectors are concurrent too. In this proof, we will use theorem 1.12 on page 32. A point is on the angle bisector of an angle if and only if it is equidistant from the sides of the angle, because this is a if and only if condition, necessary and sufficient. So that means if a point is on the angle bisector, then it is equidistant from 2 sides of the angle. Conversely, if the if there's a point, it is if a point is equidistant from the two sides of the angle, then this point must be on the angle bisector of the angle. So we can apply either way of the of theorem 1.12. So let's look at a proof here. First, what we given, we have three angle bisectors. In the picture, AF, BD, and CE. And we want to prove, first, we want to prove CE, AF, BD are concurrent. That means they intersect at the same point. The second part, the distance from G, the intersection point, to each side of the triangle is the radius of the inscribed circle. If we look at the picture here, we can see the inscribed circle this is the center, from the center to the each side, where we to each side we can draw a radius, and it's going to be perpendicular to each side. So we have two statements we want to prove. So let's prove the first one. This is one of the homework assignments, so I'm just gonna give you a hint of this, the main idea of this proof. First, we know that any two lines, if they're not parallel, they must intersect. So from the picture here, we can assume that AF and BD intersect at the point G. But we need to prove CE must pass through the same intersection point G, because CE usually when we have three lines, they may not intersect at the same point, so it could be like this, but we want to prove CE also pass through this G. We connect C and G instead of B and G here. So we apply theorem 1.12 to prove BG is also CG is also the angle bisector. So the idea is this: instead of drawing the angle bisector of angle C and show that this also passes through the intersection G, we connect C and G, and we prove the CG. So if we connect C and G and extend it, this must be through the CG must through this intersection point G. And then we try to prove CG is also the angle bisector of angle C. So that means all the three angle bisectors intersect at the same point G. So how to prove CG is the angle bisector? Then we can use theorem 1.12. What kind of point will be on the angle bisector? If we can show by this theorem, we can show that this point is equidistant from two sides of the angle. So if we look at angle C, the two sides are AC and BC. Can we show G is equidistant from the two sides? And this can be proved easily, because we already know AG is the angle bisector of A and BD is the angle bisector of B. That means this intersection point G, by theorem 1.12, the other direction, if it is an angle bisector, then it must be equidistant. So if we can draw a radius that's perpendicular to AC, which is not DG here, so if we can draw another perpendicular line, for example, we can call it GD prime and GE prime, these two must be congruent. And similarly, G is on the angle bisector of B, then GE prime, GF prime must be congruent. And if GD prime and the GE prime are congruent and also congruent to GF prime, which means GD prime and GF prime are congruent. That means, so G is equidistant from these two sides. That means G is on the angle bisector. So this is the idea of how to use theorem 1.12 to prove this theorem here. So we have to do two steps. First, what we know is, I think when we write down the given part, if we try to do this way, the given part is AG is the angle bisector, BG is the angle bisector. Prove CG is the angle bisector. So use AG and BG are angle bisector. This fact to prove G is equidistant from AC and BC. And then apply theorem 1.12 again. If it's equidistant from two sides, then it's on the angle bisector. Okay, so this is how to prove theorem 2.5, the part 1. Now how to prove part 2? Clearly from the proof of part 1, we can see that G, the distance from the intersection point of these three angles of bisectors, is equidistant to all the three sides. Then if it's equidistant from all three sides, that this G must be the radius, because it's also, when we say equidistant, what's the distance from a point to a side? It's the perpendicular line. So if it's perpendicular, that means this G must be the center of the inscribed circle, and that means the distance from G to each side is the radius.